Okay, we are in business. So here's where we were last time. Oh, also real quick, for those of you who just came in, this is leftover Halloween candy. Feel free to come grab one if you're, so inclined. Okay, so let's see here. So we were talking about this question where we're going to be looking at a curve like this, and we're interested in computing how much work it takes to move along this curve given forces that are being applied. And we have this old formula, work is equal to force dot displacement, which again was an improvement already over our sort of scalar version, unnatural, if I may say, scalar sort of version of this formula. But again, not really good enough for what we need here. The vector field might not be a constant. Usually in life it isn't. The displacement might not be along a straight line path. And again, you wouldn't expect it to be. So what we agreed last time is that we would just chop it up into little pieces. We'll look at the amount of work that it takes to move along a little piece of the curve. And, again, chop it up, add it up. Right? Fine. There is something already noticeable, though, about this particular line integral that it appears that we're developing that is different from the scalar line integral concept that we saw last time. And that is this idea of which direction we're going, right? So we're going along this curve, but very specifically, we're going this way. Right? We're not going the other way. It's totally different. Right? The amount of work that it takes to go uphill is more than the amount of work that it takes to go downhill. In fact, if you think about it, they're exact negatives of each other. Right? Okay, so weird and unfamiliar. Let's think about these other applications that we've seen. So here we had an irregular wire, and we wanted to compute the mass, among other things. Does it matter which way you add the mass? If you add as you go this way or if you add as you go that way? No, don't be silly. It doesn't make any difference at all. You're just adding, right? If you're painting the fence, does it take more paint if you go clockwise around the fence as opposed to counterclockwise? No, it's exactly the same thing. Again, silly. So there is something fundamentally different about this question. And what we call this, the indication of the direction of which way we're going along a curve. We call that the orientation of the curve. So what we're about to develop is a new kind of an integral. It is not defined on curves. It's defined on an oriented curve. The thing that we're about to define requires that there be an indication of which direction do you mean along the curve in question. Okay. All right, so with that noted, here we go. And again, keep in mind we're looking at little pieces of curve. So here we're looking at that little piece of curve right there. And just for visual convenience, I'm going to expand that down here. And look, work is equal to force dot displacement. It's pretty straightforward on that little piece of curve. After all, the force is roughly constant because the piece of curve is so small. The piece of curve is roughly straight, so the displacement is along that basically straight line. So on that little piece of curve, we're going to look at the what is the force vector. We're going to look at what is the displacement differential. And work equals force dot displacement. That's how much work it takes to move along this little piece of curve, which I will do like that. Yeah, everybody okay? Chop it up, add it up. Right? So adding this up along all the pieces. Right? That's just plugging in what the formula is for dW. And what we have now is a brand new kind of an expression. Again, we have not seen this kind of an expression before. It's a line integral because it takes place on a curve. But again, it's not just a curve, it's an oriented curve. Has to be an oriented curve. Furthermore, notice this is a real eyebrow raiser. My differential is a vector. And thus the term vector line integral. By the way, also arguably just as much motivation, the integrand is a vector field. Right? This is not a scalar that we're integrating, as we have this written here. So this is a significantly different kind of a line integral, and again, to make the distinction clear, we call it a vector line integral. Okay. All right. Let's see. A quick cultural note. I'll point out that very often people will just call this a line integral, right? And then it's left to the listener to look at the context clues and realize for themselves that this is a vector line integral specifically instead of a scalar line integral, or vice versa if they're talking about a scalar line integral. So heads up, when you hear the term line integral alone, that means that it's your job to figure out which kind of a line integral they're talking about. Okay. All right, now we find ourselves in our usual sort of quandary of we've written something down that's not really something we know how to compute. It's really more of a sort of a strategy for computation. This basically says, well, I've got this curve, yeah, and I want to chop it up into little pieces, and then on each little piece I want to write this down, and then I want to add that up, or, whatever. This does not tell us how to do that. This is just kind of a strategy. So how do we do it? Well, we've seen this situation before where we have a domain that we don't like for whatever reason. Right? In this case, because it's a curve, because it's dimensionally wrong. Right? This is a one-dimensional thing in a two-dimensional world. And that's weird. Okay. Okay. So what do? We view it as an image. We've already talked about viewing curves as images. They're parameterizations. We're going to realize it then as being the image of a particular domain. Let's see here. Probably a little bigger than that. Particular domain in the pullback space. And we're going to pull back through the parameterization. Basically the same idea as we did for scalar line integrals. And again, good news, we already have a bunch of development on this. Right? We've already developed the idea of the length of a little piece of curve. We've already developed the idea of a displacement differential, dx. We've already developed the idea of a unit tangent vector, t, capital T. And we've already recognized that the velocity, x prime, relates to these things. And again, flashing back to chapter 3 when we wrote all this stuff down, we already know these relationships between those things. This is all old news, right? None of the sort of, in this sort of middle part of the screen, none of that's new. Right? Flashback. So when we're trying to figure out how to compute this brand new, creepy looking vector line integral, it's really kind of nothing to it. The pullback of the differential, well, that differential is something I've already pulled back. I already know how to write dx in terms of t's. It's x prime dt. Keep in mind, x is the parameterization. It's in terms of t. That means x prime, also a function of t. So this is all in terms of t's. It's a pretty straightforward process. If you want to compute a vector line integral, there you go. There's your formula. And we're going to do some plug and chug on a couple of these. Well, we'll see how time works out. But we're going to do some plug and chug momentarily. But that's the big idea. It comes straight out of this picture. How we doing? Everybody's happy. For those of you who came in late, leftover Halloween candy, feel free to get up right in the middle of the lecture and help yourselves. No problem. Okay. All right. There is also the little matter of this alternative formula for dx. So, I can plug that in as well. Oh, whoops, missed. I can plug that in as well. Right? That gives us this other alternative form for a vector line integral, and you can write a vector line integral like this. A lot of people like to write a vector line integral like this. I don't care for it myself. I'm not going to say you can't do it, but I'll just point out that something kind of unnatural about this. For one thing, notice integral ds kind of makes it look like a scalar line integral, right? And it's not. It's really importantly different. The orientation matters. There's no getting around that, right? So I am of the opinion that when things are different, they should be denoted differently, right? So that's just my opinion. So there's that warning. Now, there's another thing that I don't like about this notation, and this is pretty, I suppose, quibbly. I like the fact that everything that we want to know about the domain here, this curve, it's all in the differential, right? So the integrand, I'm going to say, has nothing to do with the domain. The integrand is, well, it's defined on the domain, right? But it's not about the domain. This vector field exists independent of whatever curve you decided to draw. It exists before you even think to draw your curve, right? It's this own separate thing. It's not about the curve. Whereas that's not really the case over here. If you look at this notation over here, this is about the curve, right? ds says how long the piece of curve is. But so is t. It appears to be part of the integrand, and yet it's really telling you about the curve. It's telling you what direction the curve is going. So I don't know. That's just nails on a chalkboard a little bit. It's not wrong. It's not bad, but it's just, I don't know. It's inelegant to me. Okay. So anyway, you're going to see this, I think, even in our own textbook. All else being equal, I like this better. Oh, one other thing that I like about this. It's really very natural. This represents force. Nice and crisp. Nice and simple. Simple answer to a simple question. Hey, what is that thing? Force. Right? Likewise, with this other piece. What is that thing? That's displacement. Nice and crisp and simple. And I think that's another sort of vote in favor of this notation. Okay. So let's do one. Get our hands dirty. We are going to walk counterclockwise along the top half of the unit circle. So there's our path. Note there's an orientation indicating that we are going counterclockwise. And while we are walking along that curve, the wind is blowing and it's pushing on me, and it's making it hard for me to walk because I have to push against the wind as I walk. As you walk, you have to push against the wind. Okay. All right. So the question is, how much work do you exert as you are pushing with some force as you move along a curve, as per this setup? Okay. So roughly speaking, we've already answered this question. Work is a vector line integral of force. Now, what's with the minus sign? This is an annoying fact of reality. You have to worry about this all the time. This question was stated in a way that, as it turns out, is not natural for what we're interested in doing. That said, it's also expressed in a way that is perfectly reasonable, right? It didn't happen to be convenient for what we're doing, but there's really nothing wrong with the way this question's phrased. So, in particular, the force is given as what the wind is doing to you, right? So if the wind is blowing this way and exerting a force on you this way, of course what that means is that you have to exert an exact opposite force against it to keep the wind from blowing you over. Right? Does that make sense? In the same sense that if I hold up this pen here, there's two forces. Gravity's pulling it down, I'm pushing it up. Right? So now, the question I've been asked is about the work that you exert. So if we want to know the work that you exert, then we need to make our integrand the force that you are pushing with. The wind is pushing with this force F. You are opposing it. You are pushing with force minus F. Does that make sense to everybody? Now, please don't make the mistake of thinking, oh, okay, great, so if the question's about work, I should always throw in a minus sign. No, not at all. Depends on how the question is phrased, right? So you, as the recipient of the question, you have to look at the phrasing, see what you've been given, interpret from how it's phrased. Wait a minute, what was I just given? Which of these two negative things am I given, and which do I need, and do I need to throw in a minus sign? Okay, so heads up on this minus sign. You just have to kind of think it through every time. Okay, all right. So how do we compute these things? Well, we parameterize, and then we pull back using this formula. Okay. Well, let's see here then. Counterclockwise, top half of the unit circle. Oh, and look at that, I missed it again. Top half of the unit circle. Here's my parameterization. Now we got lucky on this one. This parameterization happens to be something that I already, this curve I wanted to parameterize, something I already know how to parameterize. So I can just kind of write that down, right? And I already remember that, previous discussions that this, in fact, does parameterize counterclockwise. And I remember where t equals 0 is and where t equals pi is on this parameterization. So the top half is just 0 to pi. So again, starting with a freebie, I'll talk a little bit more later about how to deal with it if things are a little bit different. But for the moment, we have our parameterization. We see that we're going to need to know x prime. So we compute x prime, nothing to it. It's just a matter of taking a derivative. Okay. And now it's plug and chug. So again, work is that vector line integral, which is this per the formula on the previous page, which I can simplify by recalling that I've already computed x prime. X prime is that. My vector field, f, y comma negative x, again, that was given right there. Right, so that's just kind of plugging in for that. Here's where things do get just a little bit tricky, and it is easy to get lost with minus signs. Notice there's a minus sign here. There's another minus sign inside of there. And then, so wait a minute, is it, do I want the x or the minus x or the y or the minus y? Just be careful, right? Don't try to do too much too fast when there's a lot of minus signs flying around. You could lose track and oops, a minus sign, and of course that's a problem. So when we plug in, what I'm going to do here, just for the sake of the most maximum transparency, x cosine t, right there in the formula for the parameterization. Notice I'm just going to plug that right in, this x cosine t. And likewise, of course, y is sine t, and again we'll just plug that right in, not trying to do too much too fast here. Y is sine t, and everything else is single variable calculus. Everybody good? Very pluggy chuggy. Okay. All right. Now we saw with scalar line integrals that how you parameterize doesn't matter. And it's tempting to say that the same thing is true for vector line integrals, and it almost is. It's not quite. It does matter a little bit how you parameterize. And you have to keep in mind here, your integrand is not a curve. Your integrand is an oriented curve. So when you parameterize, you have to parameterize respecting the orientation. You have to parameterize in the direction that the orientation is going. Otherwise, you're going to be going backwards, right? So that said, as long as your parameterizations go in the right way, cool fact, parameterization doesn't matter. Parameterize however you want. Doesn't matter. As long as you get the orientation right. Okay. Yeah, the big takeaway here is that this is what you have to watch out for. Make sure that you parameterize in the correct direction. Okay, now what happens if you parameterize the wrong way? How bad is it? Well, all your differentials are exactly backwards. That means there's a minus sign that shouldn't be there in every term in your Riemann sum, which means there's a minus sign in your final answer. In other words, you're just going to be off by a minus sign. So the case could be made that this isn't even really such a bad thing. Sometimes this can be helpful. It's so easy to deal with, right? So here's this stated as a theorem. Now, just as a notational point, this little superscript of a minus sign just means same curve, opposite orientation. A little bit of notational convenience. And with that in mind, what the theorem says is that when you go backwards, you will just get the negative of the otherwise answer. All right. So let me show you how you can use this. Here is a separate question. Same setup as the previous. Still with the forces and the wind and the direction and the top half of the unit circle, et cetera, et cetera. The only difference being, what if I'm walking clockwise this time instead of counterclockwise? Right? Okay, so I guess it's a different orientation. That means it's a different oriented curve. That means that we kind of oughta, in some sense, reparameterize the whole thing, go through the whole process again. The clever move, though, is what we were just talking about, is to just say, oh, well, look, this is the exact same curve. Everything's the same except for the orientation. We know that this curve, just being the opposite orientation, that opposite orientation is just going to amount to a minus sign. And the original curve that this is the opposite orientation of, we've already computed that work, right? The amount of work that it takes to move along our original curve C, yeah, we've done all that algebra. The answer was pi. So if you're going the opposite direction, you're just going to get the opposite answer. So boom, minus pi, answer, done. Don't have to reparameterize anything. It's a pretty slick move. Is everybody happy? All right. Now, I am going to come back up here and show you the stuff that I just skipped. It is nice to have some tools in your toolbox for how to parameterize. So I'm going to show you a couple of different ways to think about how to parameterize this curve where we're walking, again, clockwise. Right? So we're going like this across the unit circle. So one way you can think about it, I'm going to give you two approaches, two tools. So the first idea is to say, all right, well, here's where I am at some moment. How would I describe time if, in fact, I am walking clockwise? I'm going to say T is that angle. I mean, as I walk clockwise around this circle, here's where T equals 0. And as I move along, I'm going to say this is T equals pi because, well, that's, an angle pi later. Seems like a reasonable choice. Everybody okay? All right. Now, how can I use trig then to describe the coordinates of this point? Keep in mind that's what a parameterization is. A parameterization tells you position as a function of your parameter, and I've got a clear indication of what my parameter t is there. So cool. So let's start doing trig, which I guess we could do, but trig's not really set up around this green angle. That's not, sine and cosine are defined in this other very particular way. Sine and cosine are defined in terms of that angle. And notice green and blue kind of go in opposite directions, and notice that they always add up to pi. That means that the green angle is t, then this blue angle is just pi minus t. And so good news, it's really easy to write that position in terms of our standard theta blue angle there. Position is cosine theta comma sine theta. Is that cool so far? And then you just have to remember your angle addition formulas. You'll recall that I've made the observation that comes up, right? It won't go away. Angle addition formulas regularly and routinely useful. So please do make sure you know those. I'm going to call that a requirement of the course. I just I need to be able to use those and to in class and on exams and stuff. So make sure you know that. How y'all feel about this parameterization here? All right? Okay. Let's see here. Let's talk about this other parameterization. Here's another really slick idea. Very clever. Here's what I want to parameterize. I want to parameterize going clockwise around this circle. Here's the thing I already know, though. I already know how to parameterize counterclockwise. And I can see a pretty clear relationship between these two parameterizations. This green curve and this blue curve, they are reflections over the y-axis of each other. And so, cool, if I want to know how to parameterize the green curve, I'm going to note that it is literally the reflection of the blue curve, which of course is super easy. This blue curve is our old friend, right? Counterclockwise, unit circle, and all that. So cosine and sine, nothing to it, right? So the blue is a freebie given. The green is just a reflection of that. And so now you just have to think in terms of what does this reflection do, and not hard to persuade yourself. Geometry argument. It just puts a minus sign on the x-coordinate. Everybody buy it? It's a different way of coming at it. So which do I like best? Frankly, I like this one best, where I just make a reference to the previously solved problem and throw in a minus sign, right? That's hard to beat for convenience. But when it comes to, let's suppose I had not already done the counterclockwise. Which one of these parameterizations do I like best? I like both of these as tools, because sometimes one makes more sense than the other. Not every question we'll be interested in will involve specifically the unit circle, right? So both of these are good tools to have, ready to go. So make sure to understand, please, both of these methods. Yeah.
Would it be wrong to just use your old parameterization but set t to go from pi to 0?
Yeah, no, I hear you. Oh gosh, is it wrong? It will get you the correct answer. But I have some questions about what you meant when you wrote that down, right? Now, if the reason that you say, well, pi to 0 instead of 0 to pi because we're going backwards and that's a minus sign, then really you're making this argument, but you're putting in the minus sign in this mysteriously awkward way. You know what I mean? The other interpretation, and I kind of... I think on some level, some students really think in these terms. They're thinking, oh, well, I'm going backwards, so it's like time is moving backwards as I walk. And that's very sci-fi to me, right? Like time travel, right? So I think a good general rule of thumb when you're doing a math or physics problem is try to stay away from time travel, right? And so it just, but I know where you're coming from, right? But it's always just kind of bugged me. I think it's an unnatural argument. Is that satisfying?
Yeah.
Okay. Is everybody okay with that? Got it. All right. Good. Okay. So, line integral. Been talking about these. Vector line integral. Okay. What we've seen is that if your vector field represents forces, then the line integral represents work. In fact, this is our whole motivation for writing down line integrals in the first place. Nevertheless, vector line integrals are a mathematical construction. Vector fields do not have to represent forces. So, pretty reasonable question. What if instead, if our vector field represents a fluid flow, then now... what does a line integral represent? And again, we've got no forces in the picture at all. The vector field represents a fluid flow. There are no forces. What does a vector line integral represent? It's not going to be work. So, reasonable question. Now, this is a weird answer that I'm going to give you. I think this is a really good way to come at it, though, because there is ultimately a weird answer. All this down here is just recall. This is just to have convenient for reference if needed. What I'm going to do is I'm going to ask a seemingly unrelated question. And it's going to turn out that the answer to the question I'm about to ask is going to be a vector line integral. So you may recall I've talked in the past about sometimes the reason we're interested in a mathematical object is because it's the answer to a natural question. I'm going to be creating an interpretation by finding a question to a natural answer. One way you can kind of think about it. So anyway, point is I'm going to ask a question. It's going to seemingly come out of nowhere, but don't worry, it's going to connect up in just a minute. All right, so here's our question. Let's suppose we have a curve C like this. And let's suppose we have a cross-section area like this that I'm going to imagine that I kind of drag this area along the curve like that, and that's going to make this this kind of thin sort of tube-like region. Something like that. And that's going to be our region R, if you will. Okay, so with that set up, here's the seemingly weird, unnatural question that I'm going to ask. If I look at all this fluid in R, to what extent is this fluid flowing along the curve? That seems kind of weird. Right? But that's my question. Looking at all the pieces of fluid. So there's some fluid over here, there's some fluid over here, some fluid over here. We're going to look at each little piece of fluid. We're going to ask, to what extent is that flowing along the curve? And then we're going to add up over the entire curve. Again, not knowing really particularly why we would care about such a thing. Right? All right, so, okay, no big deal as it turns out. Here's a little piece of fluid. That little piece of fluid has volume dV. If it is flowing with a certain velocity, well, yeah, but I don't really care about the actual velocity. I just want to know to what extent is it flowing along the curve. That's a component. Right? So this weird question that I'm asking, this weird question here, whatever that is, a little piece of this thing that I'm interested in is computed by this real simple formula. It's just looking at one little piece. I have a yellow volume. I have a blue component of the velocity along the curve. And each of these I can rewrite. The component is a dot product with the unit tangent vector. Volume is area times length. Nothing really particularly exciting happens there. So I then take this little piece of what I'm interested in, and when I add that up over the entire curve to get the total rate of the fluid flowing along the curve. Again, for whatever reason, not clear why we care about this. But you can just write this all down and kind of move along, and here's what your answer ends up being. Now, we're not done yet. This is just kind of the answer to the question, but now I have to explain why we care about this strange answer to this strange question. Nevertheless, this is the strange answer to the strange question. Is everybody on board so far, at least? Okay. So why do we care about this? Well, let's just parse our result here. And let me get rid of all the distractions. Looking at this equation, what we have is that the line integral represents per unit area of cross-section, it represents this thing. It represents the extent to which the fluid is flowing along the curve. So the weird question that I asked, now again, there's this business about per unit area. Obviously, if there's more area, there's a thicker tube, means there's more fluid, and more fluid, of course, means more fluid flowing along the curve. But factoring out this business about the dependence on area, the line integral is really kind of doing the heavy lifting of figuring out to what extent is this fluid flowing along the curve. And so this is the answer to our question back here. Our question back here is what in the world is a vector line integral if we're talking about fluid flows? And the answer, again, right here, it represents how much the fluid is flowing along the curve. Everybody all right? Okay. All right. So here's a couple of examples to look at. Let's consider, I got ahead of myself just a little bit. We're going to consider a special case, an important special case where your curve is a closed curve. A closed curve just means that it kind of literally closes up on itself, so it starts and ends at the same place. When you have a closed curve, we give a special name to the vector line integral. The vector line integral is called circulation. And I'll be able to motivate that momentarily. But okay, so let's look at an example here. So we have a curve. In particular, note it's an oriented curve. This curve is going, as indicated, it's going counterclockwise. We have a fluid flow. The fluid flow, let's see. You know what? I just messed up my colors. This should be blue. Of course. That's my closed curve. My fluid flow here, F, you can see I have this going like that, and et cetera, all the way around. And now let's just kind of look at it, right? Let's look at this little piece of curve right here. Along this little piece of curve, the curve is going this way. The fluid is going the same way. Looking in this one little section here, the fluid really is flowing along the curve. And you can ask that same question every sort of little piece of the curve, and the fluid is flowing positively along the curve all the way around the curve. And so we should expect that in this case, this thing called circulation, you would expect that to be positive. And exactly how much is, we need to know the vector field in the curve. We'd have to parameterize, blah, blah, blah. You'd have to actually compute it. But just geometrically speaking, this is what positive circulation looks like. Yes? Oh, I'm sorry. I thought that. Okay, no worries. Did you want candy? Because okay, you got some. Okay, anybody else? Everybody? Don't forget free candy. Okay, so why do we call it circulation? I think there's a pretty reasonable answer here. Notice that this closed curve, well, in this case, it's literally a circle, right? It doesn't have to be literally a circle, but what you will notice is that any curve that closes, it has to kind of wrap all the way around, right? It has to, the direction that it's going has to go all the way around what you might call a circle. This integral that we're looking at is measuring the extent to which the fluid is doing that same thing. The extent to which the fluid flows along the curve. Well, if the curve makes a loop, we're talking about the extent to which the fluid makes a loop. So I think the term circulation really does make sense given that point of view. Everybody good? Yeah.
Does this have anything to do with curl?
It does, yeah, and we're gonna. That's a very good observation, and we are going to get to that a little bit later. It'll be next week after the exam, but yes, absolutely. What it has to do with curl is a whole conversation, and so yeah, I'm gonna delay your question to next week. Yeah. Okay. All right. Okay. Let's see. Let's look at this other couple of examples here. Looking at this example here, notice that my curve this time is going the other way, while my fluid is still doing the same thing. And what would we say about this? Well, here, the curve is going that way. The fluid is going sort of exactly the opposite way. So is the fluid flowing along the curve here? Well, it's going opposite of the curve. I think it'd be reasonable to call this negative flow along the curve. Right? And again, if you look at an explicit example, that dot product would literally be negative. So in this case here, the circulation, purple, you should expect it to be negative. And then looking at this last example here, this is kind of an imponderable almost. So it seems here anyway. Curve like this, and what's unfortunate is that in some places the fluid really is going what you might call positively along the curve, such as in this general area part of the curve. It's not exactly the same direction the curve is going, but it's a positive component in the direction that the curve is going. Whereas by comparison over here, the fluid is going kind of that way, the curve is going kind of this way, and again, you'd feel like it should be kind of negative over here. And so when you're computing the circulation around this green curve, there's going to be some positives, there's going to be some negatives, and it is not immediately obvious how it's going to win out, right? Is there more positive than negative, more negative than positive? There's some analysis that would need to be done there. So, won't always be perfectly obvious like these first two cases. Last quick observation about circulation. This is just a kind of an intuition thing, but when you're looking at a small object, the idea of small is that nothing's really changing all that much. There's a consistency across the entire object. So I like to throw in the term small here. Whenever you see me talking about something being small, it's because I want to make some case of what I see happening in one location. It doesn't mean everything's exactly constant, but it means that there should be a consistency of sorts. So with that in mind, what would I conclude from the fact that along each piece of curve, the fluid is flowing along the curve, and if there were some sort of grip that the fluid has on the object on this curve, right? I would kind of expect that this fluid would be pushing in the direction that the curve is going. And so, for example, if this were a fall leaf, right? Nice orange, pretty color we're getting these days. If there was a fall leaf that had dropped into a little stream, and if the water was doing like what I have in blue here representing the vector field, well, you'd expect that this flow of the fluid along the outside edge of the leaf would be rotating the leaf counterclockwise. Right? I mean, it is an easy experiment to do, by the way. You just take a bowl of water and stir the water, right? Let's say counterclockwise like this picture, and then just take a dead leaf and drop it right in there. That leaf will start turning, right? Pretty plausible. Now, of course, there's also the inside of the leaf, right? Circulation's all computed along the outside boundary, and so there's also the question of what's happening on the inside. That's where this word small kicks in. The idea is that, again, sort of a consistency. There's nothing particularly weird, like it's pushing it the other direction on the inside, and then on small things, we don't have to worry about that. Okay. All right. Okay, let's see here. I believe I have a couple of quick examples to do here real quick. We should be able to get through this page, I think. So sometimes you get lucky with geometry, keeping in mind that when you're looking at a line integral, the vector field is something that you can just draw a picture of. Right? In this case, this vector field, you'll notice it points in the direction of the position vector. So the vector field has to be what I'm going to call radial. And actually, let me make a better color choice here. The x vector, the position vector, pointing directly outward from the origin, means that our vector field F also, like a scalar multiple of that, radially outward from the origin. Yeah, cool. Easy little geometric observation. Next observation, I've got a pretty wacky curve here. Right? This is a parameterization of sorts. I guess you could call this a spherical parameterization because I'm not giving you x, y, z as functions of time. I'm giving you rho, phi, theta as functions of time. And this is a pretty scary looking curve then, right? Because how do I find x, y, and z? Well, I do a bunch of trig to my spherical coordinates. Right? So the x, y, and z is even uglier than this. So that said, convenient observation to make is that, this can be as ugly as it wants, but rho is always 1. That means that my curve, however wacky, is always on the surface of the sphere. And if my curve is always on the surface of the sphere, then the direction that I'm going is always tangent to the surface of the sphere. Is everybody okay with that part? So cool. All right. Well, my vector field is radially outward. That means perpendicular to the sphere. My dx is always tangent to the sphere. And so what can I say then about this dot product f dot dx that is my line integral? Well, here's f, there's dx, and they are geometrically clearly perpendicular, which means that this dot product is 0, which means my integral is 0. And I don't have to deal with all of the horrifying ugliness of this nasty spherical parameterization. Yikes, right? Not my problem. So heads up, be on the lookout for freebies, right? Back in the old days when I was doing those physics classes, this kind of stuff comes up. This is not a rare manufactured circumstance. This is out there regularly. So for those of you who are engineers, for those of you who are physics majors, really good idea to be on the constant lookout, constant head on a swivel for symmetry, for geometric good fortune like this, and other little bits of goodie that I'm going to point out over the rest of the course. Last little quick observation I'll make is about what we call coordinate line integrals. This is mostly a notation. Dx, old news. And we left it at that most of the time, right, previously. But look, I could just kind of flesh that all out. And it's just kind of straightforward then to point out that your dx vector has coordinates that are dx, dy, dz. Individual coordinates. Okay. When you move when your position changes by some amount, your x-coordinate changes, your y-coordinate changes, your z-coordinate changes. It's like a pretty expected result. So all we're going to do here is notice that if you just plug that in, if I just say, look, dx has coordinates, and if I look at my vector field, and if that vector field has coordinates, I can write those down. And then I can just straight up crank out this dot product. And that dot product turns into that. So all together then, now again, I haven't really done anything, right? This is not a new kind of Riemann sum or anything like that. It's really just kind of a notational sort of expansion of what we had already. And so punchline, this is just a notational alternative. Now, why would we be interested in this notational alternative? Let me start with the negative side of the ledger. This is more clunky to write down. It's more cryptic, right? If you look at our original notation over here, F is the force or the fluid flow. It's something physically natural. Dx is my displacement. It's something that's physically natural. This is actually happening. What is Q? Right? It's part of something natural, but it itself, by itself alone, is really not telling the story of what's happening. Q is kind of a weird thing, and so is R, P, etc. So this is a clunky and unnatural notation as we're seeing it here. So why in the world am I wasting your time with it then? And there's two good reasons. One is this notation here is basically what differential forms look like. And I'm not going to be able to tell y'all in this course what differential forms are, but they're a really powerful idea, extremely powerful idea. They allow for doing some stuff in multivariable calculus that you just can't do without it. There's several places in this course where I'm going to have to say, well, trust me. And the explanation, if you really wanted to fill in those blanks, would be a very long and sophisticated conversation involving differential forms. So this notation is suggestive of something extremely important. It's just not going to come up in Math219. That said, because of this cultural point, this notation is in common use. And that means that whether you like it or not, you're going to see this notation out there. Whether you can make use of this power or not, you are going to see this notation out there. So when you see this notation, just remember it's just a notational alternative for vector line integral. That's all it is. Okay, see y'all later. Have a good Wednesday. See you on Friday. Don't forget exam on Friday. And see you then. Don't forget free candy. Come grab a piece on your way out.